So now we just need to ensure that we manage to get we manage to recover S from these samples, right. So here we won't spend much time, so we will just say that so if A and B are sampled from 0 to S minus 1, IID and uniform, then the probability that GCD of AB being 1, this is some constant. Okay. So, as long as GCD of samples gives us N over S, we can recover S. Okay. So, recall that N here is known. Okay. So, yeah, that is it. So, we are done. So, we just need to repeat this and compute the GCD and we are done. So, I am not proving this claim, you can look at it offline. So, can someone review for the class what we did in this algorithm? First we prepared an input superposition of inputs, then we add zeros, sure, then we apply the oracle, okay. So far it is standard, then measure the function or the function output, right. So, this collapses it to one color. This collapses the inputs to a superposition of all those points that have the same color, I mean who map rather to the same color, okay. Now we take the QFT, okay. So, once again the crucial thing that gets achieved by taking the QFT is that we achieve independence of colors. So, therefore, whenever we repeat the experiment, we get some state which is independent of the color. And then we did some analysis to show that in fact, when we apply the QFT, all the probability goes and sits on points which are multiples of N over S. This is really important, right. So, we had sort of whatever state we had, I mean we said that the inputs are separated by multiples of S. Now by applying the QFT we get all our probability on points that are multiples of N over S, okay, and this is independent of the color. So, every time I perform the experiment, even though when I measure the second register I may get a different color, right, the distribution after that does not change, right. So, now whenever I sort of apply the QFT and then measure the first register, I get some gamma which is a multiple of N over S, and this is enough for me to recover first of all N over S, because I mean I have to get rid of these multiples of N over S, that I will do just by computing the GCD. We made a quick claim without proving that there is a constant probability for the GCD to be 1. So, if the GCD is 1, that will give me N over S, right. So, the GCD of whatever k N over S and k prime N over S will become N over S whenever k and k prime have GCD 1, and because I know N, this helps me to recover S. Okay, so this algorithm, like I said, is going to work even if I do not know, even if my function is not exactly periodic. Okay, so we will see that when we look at Shor's algorithm, we need to extend this analysis. So, it is a little bit more messy, okay, but essentially the same ideas will work. So, that is why I thought that it is cleaner for us to just look at Simons over Zn, and now what's going to happen with Shor's algorithm is that, you know, I don't, like when I prepare my input superposition, I don't actually, ideally I would have liked to prepare the input superposition of like for phi, for n, for, you know, phi of n. So, or okay, for a second, so let's think of the number m as pq that I want to factor, right. So, in this algorithm we were using you know, we were preparing a superposition over capital N inputs, right. So, ideally what we would have liked to do for Shor's, if we could, you know, if we could, would be to just prepare a superposition over phi of m inputs. But obviously we do not know phi of m. So, this is because as we saw, I mean, we do not know how to compute phi of m without knowing the factors in the first place, right. So, that is why we are going to have to extend this analysis to, we'll basically what we'll do is we'll make some approximation for phi of m. We'll just choose some very, very large number, okay. And then what will happen is that, you know, the function will be periodic, but we won't have this guarantee that, you know, it will fit exactly. So, because I chose some weird sort of upper bound on which to run this, right, this periodicity, it may kind of it won't respect the boundary. So, it may fall short or go off, right. So, this algorithm has to extend to that approximation, and we'll just see how to make modifications to make this work. Okay, so are there any questions? But I hope that this algorithm was clear to everyone. And this will also solve the discrete log problem, because you know, the discrete log problem is a period finding problem. So, we will end the lecture here, but I will just as a, you know, just as a aside, let me just say, so if I, you know, if I have g to the s, right. So, remember the discrete log problem, right. So, I have some group generator g, okay, and I have some you know, I compute h as g to the s. Let me use a different thing, alpha, let us say, right. So, now can you tell me, I want to find the discrete log of h. Can you tell me how to represent this as a period finding function? Given an h, I want to find the discrete log, right. So, note that it's not enough for me to just find the period of I mean, I already know the order of this group, right. So, there is no secret over there. What I need to do is define a function which somehow incorporates a given h in it, so that finding the period of that function gives me the discrete log of h. You see why your suggestion does not work, okay. So, you can think about this. So, so this does not work, right. So, I need to define a function which has h in it, and it should be I mean, this function should somehow capture the fact that finding the period of that function gives me the discrete log of h. So, you can think about this. So, I think we are almost out of time. There is also a logical point to stop. So, let us stop here. We will move on to Shor's next time. Hopefully, we can just finish it in one more lecture.